Bismillahirrahmanirrahim. We are at lecture number 9 of Mechanics of Material 2, that is about strain transformation. We will derive the equations for strain transformation and we will compare with those equations that we have derived in the case of stress transformation. First of all, we will discuss general state of strain. Figure A shows undeformed element at a point in a body. Since the dimensions of element are very small, its deformed shape will become a parallelepiped to figure B. So figure A is a cube will become a parallelepiped after deformation. Normal strain changes the side of the element to 1 plus epsilon. Normal strain changes the sides of the element to 1 plus. So if these are normal sides, delta x, delta y, delta z. X's are shown here, x-axis, y-axis, z-axis. So this delta x side has changed to, after deformation, 1 plus epsilon x into delta x by applying the definition of normal strain. Delta y will become 1 plus epsilon y into delta y. Delta z side will become 1 plus epsilon z into delta z. So which produces a change in the volume of the element. So the change normal strain will cause change in volume. As long as shear strain are concerned, shear strain changes the angle between the sides of the element too. So if normally this angle was pi by 2 or 90 degree, and after deformation this has become pi by 2 minus gamma xy. So this shear strain has occurred at this angle. This angle pi by 2 has become pi by 2 minus gamma yz, and this angle pi by 2 has become pi by 2 minus gamma xz. Shear strain changes the angle of side to these sides, which produces a change in the shape of the element. As was in the case of stress, same is for strain. There are three normal strain components, epsilon x, epsilon y, epsilon z. There are three shear strain components, gamma xy, gamma yz, gamma zx. Like stress, these strain components also depend on the orientation of theta. Remember, plane stress not implied as plane strain case due to Poisson effect and vice versa. As figure shows, plane stresses sigma x, sigma y do not cause plane strain because epsilon z is not equal to 0. If you look at this, how many stresses are being acted to sigma x and sigma y, and these are acting in a plane. So this is plane stress case, but effect of this will cause this strain, epsilon y strain, and also epsilon z strain. That's why plane stress does not cause plane strain. Actually, a case of plane strain rarely occurs in practice, but analysis of plane strain is still of great importance because it will allow us to convert strain gauge data measured at a point on the surface of the body into plane stress at the point. So by having this analysis, we can convert strain gauge data to plane stress at the point. Now we are coming towards derivation of general equations for plane strain transformation. These equations are used to determine the components of normal and shear strain at a point at some arbitrary angle theta. That's why these will be called as epsilon x prime, epsilon y prime, gamma x prime, y prime, provided the components epsilon x, epsilon y, gamma xy are known. So if these parameters are known, we have to find out these parameters, and angle theta is given. For that, we will do something to derive the equations. Before deriving, we should know the sign convention, and these are: normal strain epsilon x and epsilon y are positive if they cause elongation along x and y axis respectively. Elongation positive, normal strain positive. Shear strain gamma xy is positive if interior angle that was originally at 90 degree becomes smaller than 90 degree. So if angle is smaller than 90, then shear strain will be positive. This sign convention also follows the corresponding one used for plane stresses sigma x, sigma y, tau xy that we have done in the previous some lectures. So these sign convention are in accordance with that is positive will cause the element to deform in the positive epsilon x, epsilon y, gamma xy directions respectively. Counterclockwise angle is taken as positive. So theta is always positive when it is taken as counterclockwise. So all the discussion that we have made are shown here. So if this is the original diagram, after deformation this has become like this, and here this is epsilon x and this is epsilon y, and both are positive. So positive angles are shown. This gamma xy is positive, this angle. So because this angle and this angle, because this is up now, it is less than 90 degree. These are x-axis, y-axis. After rotation, counterclockwise theta is positive, x prime and y prime axis here, and after rotation this has been shown here. So these angle are gamma x prime y prime by 2, gamma x prime y prime 2. So these shown here at rotated axis along x prime and y prime. So along x prime, this is epsilon x prime dx prime, and this is epsilon y prime into dy prime. So these are unknown, and we will find out these epsilon x prime, epsilon y prime, and gamma x prime y prime. So these were known. So this was known, but after rotation theta, these are unknown, and we will find the relation of these parameter with this. Normal and shear strain. To determine epsilon x prime, normal strain along x prime axis, and shear gamma x prime y prime. Consider the figure. This is very simple figure. This dimension is delta x, this dimension is dx, and this dimension is dy. So along this x prime axis, this is dx prime, and here angle is theta before deformation. So if this angle is theta, these dimension is given, then from this diagram it is very easy to find out this will be the cos component of dx prime. So dx is equal to dx prime into cos theta, and as long as this is concerned dy, that will be sine component. Dy is equal to dx prime into sine theta. We will use these in equations to simplify equations. First, the effect of normal strain epsilon x, that is known parameter, on dx prime elongation. To find the epsilon x prime, first of all we will find the elongation, the change in the delta x prime. When positive normal strain epsilon x occur, dx is elongated. So if normal strain positive is there, it will elongate it like this, and elongated value is epsilon x into dx, which causes, so the share of this along this axis, this is the whole, and we have to find the component along this x prime axis, so which causes dx prime to elongate. So dx prime along this elongation will be, so if this angle is theta, this is the hypotenuse, this will be cos component, so it will elongate epsilon x dx into cos theta, and it is in positive expression, that's why it is positive. Second, the effect of normal strain epsilon y on dx prime elongation. When positive normal strain epsilon y occur, dy is elongated by this. So this was normal and this is elongated, and this elongation is epsilon y dy according to definition of normal strain. And the component of this along x prime axis will be this red one, that is epsilon y dy into sine theta. If this angle is theta, so it will be sine component, very easy. So this is shown here. Then third, the effect of shear strain gamma x y on dx prime elongation. Assuming that this dx remain fixed in position, this shear strain gamma x y, which is the change in the angle between dx and dy, so change between, so there is no change here, we have assumed just to simplify our analysis. So this dy will, tip of this will go here because this is fixed according to assumption. So change in angle between dx and dy cause the top of the line dy to be displaced by angle into this dy. So angle is gamma xy into dy. So this has been elongated, displaced right to the right, positive, along positive x-axis. So if this is the full component of this along x prime will be shown as this red line, and this will be cos component because this angle is theta, this angle is theta here. So this will be gamma xy dy into cos theta. Remember, we have to find these. So for that, for first one, and these are known, so effect of these known we have done here, 1 2 and 3. So adding all these effects, if all three of these red elongations are added together, the resultant elongation of dx prime is then, if you look at this was positive, this was again positive, and this was again positive. So delta x prime, delta mean change in this dx prime, delta x prime is equal to epsilon x dx cos theta plus epsilon y dy sin theta plus gamma xy dy cos theta. So we have added up all these three red lines from equation given at slide 6. Dx was this and dy was this, so just put the value of dx here, dy here. So I have put it here, epsilon x prime is equal to, so this one, put this one, and put this one. So in this equation, right side has dx prime, dx prime, dx prime, so this can be taken as common, and when we shift here it will be divided. So now it becomes delta x prime over dx prime is equal to epsilon x cos square theta, cos has been, plus epsilon y into sin square theta plus gamma xy into sin theta cos theta. Since we know, according to definition of strain, change in length over original length, so change is delta, original var d, so this will become epsilon x prime because this is along x prime axis. So when we put here, this equation will become epsilon x prime is equal to epsilon x cos square theta plus epsilon y sin square theta plus gamma xy into sin theta cos theta. And from trigonometry we know cos square theta can be written like this, so I have placed here. Sin square theta can be replaced by this, and 2 sin theta cos theta is equal to sin 2 theta, so sin theta cos theta can be replaced. So first of all multiply and divide by 2, so this will become sin 2 theta. So from here epsilon x prime is equal to, so this 1 by 2 into epsilon x, and this is also 1 by 2 into epsilon y, so this can be added up in first term. So epsilon x prime is equal to epsilon x plus epsilon y by 2, remaining is cos theta again these, so but here it is negative, that's why epsilon x minus epsilon y by 2 into cos 2 theta, and this will become plus gamma x y by 2 into sin 2 theta. And we have derived first equation, that is for normal strain along x prime axis, and this is equation 10.5 from R.C. Hibbeler book. So for normal we have done. For shear it is easy, if you have understand the previous one, it is very easy. For gamma x prime y prime shear strain, to determine gamma x prime y prime, we must find the rotation of each of the line segment dx prime and dy prime when they are subjected to shear strain component epsilon x, epsilon y, gamma xy. First, we will consider the counterwise rotation alpha of dx prime, figure E. So at this figure, this rotation is given as alpha, and alpha will become equal to delta y prime over dx prime from trigonometry. L is equal to r theta. So having that relation, we can this. So the displacement delta y prime, this will be due to three displacement component due to this, this, and this. So we will do that. And as long as this is concerned, that is rotation of dy prime. So after rotation, this will become beta. So change of alpha minus beta will be the shear strain gamma x prime gamma prime. So if you look at closely look at this, this is along x prime axis and this is along y prime axis. So if we change theta by theta plus 90, we will have this relation beta. So we will do it later. So again, coming to the points, rotation of dx prime is considered, and that has caused alpha, and alpha is equal to delta y prime over dx prime. The effect of normal strain epsilon x on delta y prime. The effect of normal strain epsilon x on delta y prime will be minus epsilon x dx sine theta. How I have written? So if you remember, we have discussed this diagram. This is the change or strain in this direction dimension dx. So this will have two components. One is red, that we have discussed in the case for normal strain epsilon x. So now we are considering this oval shape, red oval shape highlighted component. So this will be the effect of this normal on delta y prime. So this will cause this, because this is along y prime axis. Next, the effect of normal strain epsilon y on delta y prime will be, so if you look at this we have discussed here in the some previous of the slides. So it's that component that is along y prime axis is epsilon y dy cos theta, and this is positive. If you look at this was along minus, that's why minus is written here. But in the second case, it is positive, that arrow is upward, arrow is along y prime axis, that's why it is positive in figure C. And the effect of shear strain gamma xy on delta y prime will be, so if you look at this has the hole, and this will be considered now that is along y prime axis, and it is along negative, that's why minus is written here, and that is gamma xy dy sine theta. Minus is placed because arrow is downward in the negative y prime axis. So adding the three displacement component for delta y prime, it become delta y prime is equal to minus epsilon x dx sine theta plus epsilon y dy cos theta minus gamma xy dy sine theta. So in this was negative, second was positive, and third was again negative. That's why negative, positive, and negative. After putting the values from slide 6, these values I have put here. Dy is and gamma and dy has been replaced by dx prime sine theta. So in this equation, dx prime can be taken as common and can be divided here. So when you divide here, and from slide 11, this was equal to alpha, that's why alpha is written here. Alpha is equal to delta y prime over dx prime is equal to minus epsilon x plus epsilon y, this is into sine theta cos theta minus sine gamma xy sine square theta. When we put in this equation, when we put theta equal to theta plus 90, we will get beta, as I have discussed in this at this slide. So if you put theta plus 90, you will be at beta. instead of alpha. So putting the values theta is equal to theta plus 90 to get beta is equal to rotation of dy prime. So beta will become same, but instead of sin theta is sin theta plus 90, instead of cos theta plus 90 minus gamma xy into sin square into theta plus 90. After simplification, this is cos, this is sin, and this is cos. By having trigonometric, sin theta plus 90 will become cos theta. So this will be this one. And the shear strain gamma x prime y prime will be effect of the difference between these two angles, alpha minus beta, and that will be minus 2 if you subtract here, minus this minus this minus plus, and this minus again minus, that's why it is minus 2 into epsilon x minus epsilon y into sin theta cos theta. This is common here, and here minus and again minus, so minus plus, so cos become plus, so plus gamma xy into cos square theta, this one minus sin square theta. By having trigonometry relation, 2 sin theta cos theta become sin 2 theta, and cos square theta minus sin square theta is equal to cos 2 theta. By putting this value, we will have the final result as gamma x prime y prime by 2. We have divided whole equation by 2. Gamma x prime y prime by 2 is equal to minus epsilon x minus epsilon y by 2 into sin 2 theta plus gamma x y by 2 into cos 2 theta. This is equation 10.6. Why we have divided here? Because we have to compare with the stress, and for that here that term was divided by 2. That's why we have divided whole equation by 2, and it will be easy for you to remember. Just look at this equation. So this we have derived, and if in this 10.5 we put theta is equal to theta plus 90, we will get epsilon y prime, similarly as we have done in the case of stress. So this will be equation 10.7. So these two equations we have derived here, normal strain and shear strain. And normal stress, shear stress we have derived in the previous lectures. If we compare these equations, these 3 strain and these 3 stress equations, comparison will give us, if we replace sigma x prime with epsilon x prime, sigma x with epsilon x, sigma y with epsilon y, and sigma y prime with epsilon y prime, just normal, for normal just you have to replace, but for shear tau x prime y prime will be divided by 2, gamma x prime y prime by 2, and tau xy will be replaced by gamma xy by 2. So gamma xy by 2, and here tau. So if we replace these things, we will get strain equations from stress. So if you look at these, it is very easy to remember. So these has similar shear strain and normal strain has similarity with shear stress and shear normal stress. So this is all from my side. Thank you. Please revise these derivations by your hand for having a good practice and memorization. Thank you very much.